Hello dear students, welcome to the channel Pen and Paper Chemistry on YouTube. The subheading that we are taking up today is electrode potential and its measurement. So before we go on to describe what is electrode potential, let me just recall what we did previously. We had a zinc rod dipped in a solution of zinc sulfate, a copper rod dipped in a solution of copper sulfate. The two parts are connected by what we call as a salt bridge, and outside the current is flowing through a conducting wire. The electrons flow from zinc to copper and current flows from copper to zinc. Now if we connect a voltmeter over here, we find that the potential difference shown by the voltmeter is 1.10 volt. Now this may be sounding all French. So let me break it down first. What is this potential? Now we know that if we have a pipe which has water in it, and this has water in it, if I tilt the pipe, the water will flow down, it will flow out, right? For example, I have water in this bottle, right? Now if you see, as long as it is both the sides of the bottle are at the same level, there is no flow of the liquid. Now if I open the cap, which I had kept it closed by now, I have this bottle here, both the sides of the bottle are at the same level. Now if you notice very carefully, I am going to tilt this bottle and there is a slight height difference, and more the height difference, greater is the flow of water through the bottle, right? So when does the water flow from the bottle? Yes, when there is a height difference between the two levels. What is there is, in this bottle there is water, and this water, when the whole bottle is horizontal, then in this case the potential energy of the water at the two ends is the same. When I tilt it, now what happens is there is a difference in potential or potential energy, correct? When the water flows down, the potential energy further decreases. The same word or the same concept is applicable over here. Each of the two rods are at a certain potential. Why does this potential develop? Let us understand. The zinc rod is in contact with the zinc ions. So the zinc rod is getting converted into zinc ions by the release of electrons, what we call as oxidation. The zinc ions in turn are gaining 2 electrons and turning to zinc. So in other words, what is there is an equilibrium over here. Now because of this equilibrium, there are electrons deposited onto the rod. Because of the electrons, the zinc ions remain close to it. So we have opposite charges in close proximity, because of which there is a potential which develops, right? Same way, we have copper in contact with copper ions. There will be an equilibrium between the copper metal, that is solid, and copper ions which are in solution. Because of the loss of electrons, this copper rod acquires a positive charge. So I am going to show that plus charge on this rod, because of which what will happen now? Yes, the negative species will become attracted to it, and that is the sulfate ions over here, right? Again, because of the difference in charges, there are two ends, the plus and the minus end, because of which there will be a difference in potential between the zinc rod and the copper rod. Zinc rod is at a certain potential because of the equilibrium between the metal and the ions. There is a potential due to the equilibrium between copper, metal and its ions. The two are at different levels. When we connect them by a wire, and because of this difference in level, electrons begin to flow from zinc to copper, or what we say is that the conventional current flows in the opposite direction, that means from copper to zinc. When this is measured, the potential difference between the two electrodes, it is 1.10 volt. Now what we are measuring over here is the difference in potential between the two electrodes. It's not the potential of each of the electrodes, it is the difference in potential, right? Now unlike this water in a bottle where I can measure the potential energy mgh and mgh and gives me the potential energy at the 2 points, for each of the electrodes it is a little difficult to measure the potential of each of the electrodes, because we see the phenomena or the deflection in the voltmeter, galvanometer, or the measurement of the potential can only happen when I connect the two electrodes by means of a conducting wire, right? So how do I solve this issue? I have potential difference, and that potential difference I know by connecting the two rods. Now supposing I want to randomly try and connect two metals or a metal and a non-metal rod, then how do we go about it, right? What will act as the cathode, what will act as the anode? So this is what we need to do in order to determine the electrode potential. So how do we measure the electrode potential? So just like how do you measure the length of any object? You use a Yes, absolutely. You use a ruler, correct? You say 1 centimeter, 2 centimeter, 3 centimeter. So when I say 1 centimeter, that means it is 1 time of 1 centimeter. If I say 10 centimeters, that means it is 10 times of 1 centimeter. What is this 1 centimeter? Now this is my standard. This is the standard that is followed all over the world, and that is what we have chosen in order to measure any object. So that could be centimeter, that could be meters. In the case of longer distances, it is kilometers, and it is standard. 1 kilometer throughout the world remains the same. 100 meters throughout the world is the same. Same way for mass, you've chosen a standard, and that standard is called kilogram, right? Or gram, depending upon whichever system you follow. So when you say that the mass of an object is 5 kg, that means it is 5 times of 1 kg, and this 1 kg is the standard that I have chosen in order to express mass. So I need to use some standard over here in order to measure the potential of each of the electrodes or each of the half cell. How do we do that? For that we have certain electrodes which are considered as standard electrodes. So let's study about those standard electrodes. Reference electrodes, that means these are the electrodes which are used to measure the electrode potential of the various metals and the non-metal combinations. There are 3 types of reference electrodes that I will mention at present, that is the SHE, also called as NHE. SHE stands for standard hydrogen electrode. NHE also stands for normal hydrogen electrode, although She is a more common term which is used. The other is the calomel electrode. Calomel is a word which comes from mercury. So as the name indicates, it pertains to a combination of mercury and its ions. Silver chloride electrode. Now presently we shall limit ourselves to She, that is the standard hydrogen electrode. In the case of standard hydrogen electrode, what will happen is we will develop an equilibrium between hydrogen gas and hydrogen ions, right? So hydrogen gas will have tendency to turn into hydrogen ions by losing electrons. So this is one reaction, the forward reaction. At the same time, the hydrogen ions will have a tendency to gain back the electrons and turn to hydrogen gas. So an equilibrium is developed between hydrogen gas and its ions in aqueous solution. So because it's a gas, let me indicate it like this, and we have hydrogen ions in aqueous solution. Now this is the kind of equilibrium we are looking for. Let us balance this equation as well. So this is how we will represent it. Now hydrogen gas as a reactant means I need hydrogen over here. Now hydrogen, you know that it's highly inflammable, very light gas, so all that is there. So we have to be very particular about the apparatus that we are going to use over here. Now this blue line that you see over here, the outer, is nothing but a glass tube. Inside this glass tube we have fused a platinum wire. At the end of this platinum wire, so the effect is, so let me show you what is there inside the glass tube, is just a platinum wire, and at the end of this platinum wire there is a platinum plate, and this is coated with platinum black. Platinum black is nothing but platinum in finely powdered form, which appears slightly black in color. This is done so that we can increase the surface area of this particular plate. Why do we need platinum over here? Because hydrogen is a gas. It needs a surface where the molecule and the ions can interact. They can exchange electrons. So that is why, in order to provide that surface, and here platinum is going to act as an inert electrode. That means it itself will not participate in the reaction. Now this word, this term inert electrode, we have mentioned earlier as well. Now here, since it is only providing a platform for the hydrogen molecule and the hydrogen ions to come, and that this equilibrium to be established. Then into this tube. Now outside this we have got a glass tube, and there is an inlet for hydrogen gas. Now we notice that the electrode potential varies with temperature, pressure and conditions like that. So we need to specify the pressure and the temperature. 1 atmospheric pressure and 25 degrees Celsius, or we also call it as 298 Kelvin. Now where do we get the hydrogen ions from? If you notice over here, I have mentioned over here 1 molar hydrogen ion solution. This 1 molar hydrogen ion solution is nothing but a solution of any of the acids. The concentration of the acids is so taken that overall you will have 1 molar hydrogen ions in solution. So for example, if I am taking HCl, I will take 1 molar HCl. But if I am taking H2SO4, then in this case, if you notice, 1 H2SO4 is giving you 2 hydrogen, right? So we have to be very careful. So if I am going to take 1 molar H2SO4, it is going to give me 2 molar solution. So if I want 1 molar hydrogen ion solution, I will take, correct, half molar. Now this complete setup is what we call as the standard hydrogen electrode, or She. What is the electrode potential of this? How do we measure that? To make it simpler, just like I mentioned that we've chosen certain weights and certain distances as standards, we have chosen the electrode potential of this setup as 0. It's not that it is 0, it is not that there is no interaction, there is no exchange of ions happening over here, electrons happening over here, but we have assumed for ease of measuring the other electrodes. Why did we choose hydrogen? Hydrogen does not react with many of the metals, and at the same time, if you realize, hydrogen is one element which is capable of behaving as a metal and as a non-metal. It is capable of giving as well as losing electrons. It's one element which is put in the center of the periodic table as well. Now, this we have discussed earlier. I will not go into the depth of it. So what we've got over here is, now we've chosen hydrogen electrode as our standard, the electrode potential of which is 0, yes, volt. Please don't forget to mention the units. Now, how is this standard hydrogen electrode used to measure the potential difference or the electrode potential of the other metals? What we are going to do here is, we will set up now this particular cell in combination with the other electrode whose electrode potential I have to measure. So let me say, if I want to measure zinc, the electrode potential of zinc. So what do I do over here? I'll take zinc rod in a solution of zinc ions. So I have this in place. Of course, we will have the salt bridge. We can't forget the salt bridge. We have already talked about salt bridge in great detail in the lesson on galvanic cell or voltaic cell. Now, next thing to do is, we connect the hydrogen electrode with the zinc electrode. And we connect a voltmeter in this, right? The potential that you measure over here will be the potential of the zinc electrode, right? And we will also determine what is getting oxidized and what is getting reduced. We notice here that the current begins to flow from, go ahead, yes, we notice that current flows from hydrogen to zinc. That means, what is the direction of the flow of electrons? So we are saying current, when we see the deflection, we see that the current begins to flow from hydrogen to zinc. What is the direction of flow of electrons? That means, yes, the direction of flow of electrons is always opposite to the direction of flow of current. In other words, electrons, there are more electrons on zinc and there are less electrons on hydrogen. Meaning to say, at the zinc electrode, what is predominant is the, yes, the oxidation reaction. That means zinc is getting oxidized. So what is the reaction which is taking place at the hydrogen electrode? Yes, hydrogen is getting reduced. In other words, when zinc and hydrogen are connected, zinc has got more tendency to get oxidized. How much more tendency to get oxidized is what we measure by what we call as its electrode potential, which is 0.76 volts. So your voltmeter shows 0.76 volts over here. That means this is how much is the potential of zinc to lose electrons compared to hydrogen. So how much is it? So that means this is a measure, this particular value 0.76 volts is a measure of oxidation potential, right? Potential means capacity, oxidation, that means potential to get oxidized for zinc is 0.76 volts. Correct? Now, let me go a step further. That means how much is its tendency to get reduced compared to hydrogen? If its oxidation potential is positive, what will be its reduction potential? That means its tendency to get reduced will be that much less. So how do we represent it? Is by a negative sign over here, saying that it is negative 0.76 volts. If it has got this much capacity to get oxidized, this has got this much capacity to get reduced in comparison to hydrogen. Let me make this simpler. When zinc is changing to zinc ions, notice what I have written over here, E, Zn, Zn2 positive, the potential is 0.76 volt. In this representation, I am showing oxidation, zinc changing to zinc ions, right? The same thing I will write in the opposite direction. If zinc ions have to change to zinc, what will be the capacity? Yes, it will be the opposite sign, that is minus 0.76 volts. So I see very clearly, this is what we call as oxidation potential. Potential to get oxidized. This is called reduction potential. Potential to get reduced. So if I am comparing hydrogen and zinc, then zinc has got more tendency to get oxidized and hydrogen has got more tendency to get reduced, because the reduction potential of hydrogen is more than that of copper. How? What is the reduction potential of hydrogen? Go ahead, tell me. Yes, it is 0. So what is greater? 0 or negative 0.76 volts? 0 has no sign, right? So what is greater, 0 or minus 0.76 volts? Absolutely right. It is 0 which is greater. My negative 0.76 volts will be smaller. So in this case, what is acting as the anode? Can you give me the answer for these three questions? Tell me the anode in this setup, tell me the cathode in this setup, and the cell reaction. Three things I am asking you to give me, and if you don't know any of these terms, I would request you to see the video on galvanic cell or voltaic cell. I have clearly explained these in that. And fourth, yes, the cell representation. It will be a very good practice for you, and believe me, you will find yourself so confident in this topic that you will not have to touch your book at all when revising for the test or any exam. Once the fundamental is cleared, oxidation potential, tendency to get oxidized, reduction potential, tendency to get reduced, and I had also given you the short forms, oil rig. Yes, oxidation is loss and reduction is gain of electrons. I had also given you lone. Left hand side oxidation, anode negative. Right. Left hand side not of the diagram that we have drawn. Left hand side in the cell representation. If your concepts of galvanic cell are clear, I am sure you will be able to relate to what I am talking about over here. Pause the video and write the answers to these questions and tally with the answers that I will give you. Go ahead, match your answers. Anode at which oxidation is taking place is zinc. Cathode at which reduction is taking place is the hydrogen electrode. What will be the cell reaction? Now we know that zinc is getting converted into Zn2 positive plus 2 electrons, and in the case of hydrogen it is gaining 2 electrons in order to turn to hydrogen gas. So 2 electrons being gained, 2 electrons being lost, the equations can be added to give us the final equation as zinc solid plus 2H positive in aqueous gives Zn2 positive aqueous plus H2 gas. The fourth point, the cell representation. The cell representation, left hand side oxidation anode. So on the left hand side, I will write it represented as oxidation. Zn changing to Zn positive. Please don't forget to mention the concentration, which will be 1 molar. Because we are talking about standard measurement over here. These two double lines indicating the salt bridge, hydrogen ions, 1 molar concentration in contact with hydrogen gas, the reaction taking place over platinum, the temperature and pressure conditions to be mentioned because we are talking about the standard hydrogen electrode. And we are talking about a gas over here whose values will depend with the potential values will vary with temperature and pressure. Is the cell representation complete? Something is missing. Can you tell me what is missing in my representation? Perfect. The direction of flow of electrons, which is from zinc to hydrogen. Correct? I love the smile on your face and the confidence that you are showing in understanding this topic. Now let me change it to, let's say now we replace the zinc by copper. You know, I love these two examples as I mentioned earlier because all of you are very familiar with the activity series and you know very well that zinc is more reactive than copper, so makes the work easier and relatable as well. I don't want to give you new concepts with every diagram so that you get confused. And as a student, to be honest, I also understood with these two examples, so that when I'm confused, I just go back to zinc and copper and that's it. It's done. So don't think that I'm just, being monotonous. It helps. It really helps. Familiar turf, right? So I have got the same setup. So the hydrogen electrode, the salt bridge, the conducting wire, the voltmeter, and what do we have over here is we've got a copper rod in contact with copper ions. And don't forget to mention 1 molar because we are going to measure the standard value over here. Now, here I notice something totally opposite. That means I notice that the current is flowing in the opposite direction. Okay, I've given you a hint. Direction opposite to when I had connected zinc over here. So when it was zinc, the current was flowing from, it's not zinc to hydrogen. Zinc to hydrogen was the flow of electrons. So the current was flowing from, hydrogen to zinc. Now I am saying that the current is flowing in the opposite direction. So what is the direction of flow of current now? Correct. It is from copper to hydrogen. Now this is a big hint that you got. And what do we notice over here is that the potential difference measured here comes out to 0.34 volt. Now based on this observation, you tell me whether this is oxidation potential, reduction potential. What will be the cathode? What will be the anode? You have to give me the cell reaction. Oh wow, you are already on your way. I haven't even finished writing the questions. The fourth one definitely is the cell representation. Go ahead. Do it and then come to the video. Pause it and do it. Tally your answers. Yes, I have not written the answer on the board. For the anode, cathode, half of the answers are written, half are not. You tell me now. So, anode, left hand side, oxidation, anode. Yes, it's the hydrogen electrode which is going to behave as the anode. What will be cathode over here? Perfect. It's copper. Why are we saying like this? Yes, because the current is flowing from copper to hydrogen. That means the electrons this time are flowing from, the current is flowing from copper to hydrogen. So the electrons are flowing from, correct, hydrogen to copper. That means electrons are being generated at hydrogen. In other words, it is the hydrogen electrode which will lose electrons when copper. So till now, when it was being treated with, when it was being put with zinc, hydrogen was acting bossy. Oh, I want electrons, you have to give them to me. Whereas as soon as copper steps in, yes boss, I am ready with the electrons, I am ready to donate electrons, and there it is. So hydrogen loses electrons and copper is smart and it picks up the electrons. In other words, reduction is taking place at the cathode, oxidation is taking place at the anode, right? So cathode is our copper, anode is our hydrogen. For cell reaction, Cu2 positive plus 2 electrons gives you copper. Hydrogen changing to 2H positive plus 2 electrons. Just add the two reactions over here, the two half reactions. So we have Cu2 positive, of course aqueous, plus hydrogen gas gives you Cu solid plus 2H positive aqueous. Here the two electrons will cancel out because the number of electrons being lost is the same as the number of electrons being gained. Coming to the cell representation, again, yes, we have platinum, hydrogen ions changing to hydrogen. That means what we've shown over here is, have we done the wrong thing? Yes, we have done the wrong thing because we have shown over here reduction, whereas we should be showing, perfect, we should be showing oxidation over here. So oxidation is loss. So hydrogen gas at 1 atmospheric pressure in contact with hydrogen ions, 1 molar concentration, 25 degrees Celsius, right? So left hand side has to show oxidation. Oxidation is loss of electrons. The right hand side has to show reduction. So we've got copper ions, and because we are talking about the standard electrode potential, it is 1 molar solution of copper ions in contact with copper solid. Again, the last step in cell representation, movement of electrons from left hand side to right hand side. Please remember, left hand side to right hand side does not mean in this diagrammatic representation. Left hand side to right hand side means in this cell representation that we have got. That means the 0.34 volt that I have measured over here, the standard value that you've got, 0.34 volt, this much is the tendency of copper to get perfect. reduced. So this is what is called as the reduction potential of copper. That means this much is the tendency of copper to get reduced to gain electrons in comparison to hydrogen. Correct? So what will be its oxidation potential? Super, it will be negative 0.34 volt. Right? Now, let's go on to the next step. What's the next step? Yes, let's join copper and zinc and let's have fun. Let's see where the war heads to. Now, who wins out of the two of them? I hope you are liking the way we are learning electrode potential and electrochemistry. Be in touch, be online, because we are coming up with the next video talking about EMF of the cell. How do we talk about cathode, anode, and how do we calculate EMF? Watch out for more. Do stay subscribed and put the notifications on. Happy studying to all of you. Do subscribe for more videos in chemistry and don't forget to share the channel with friends and classmates. See you in the next video.